Mathematical explanation of bias-variance trade-off. In the previous lecture, we learned about bias-variance trade-off, what is bias error, what is variance error, and how these two errors contribute towards the total error. In this lecture, we are trying to understand how to represent bias error mathematically, how to represent variance error mathematically, and then in turn, how can we reduce it. So if you want to reduce bias error and if you want to reduce variance error, the first thing is you should be able to understand how can you represent mathematically so that you see which factor you have to reduce in order to reduce this error, right? That's only how you can reduce the error. So let us find this. We'll take linear regression as an example, and from that I'll show you how to calculate bias and variance. Let's say my linear regression equation is like this. Y cap is equal to W0 plus W1x plus epsilon. From the previous classes, you already know y cap is the target that I predicted. Y cap is the predicted target. Initially, x and y will be provided. That is, for each of the x, what is the observed y? This will be already provided in the data. What I'll try to do, I'll try to approximate this y using my linear regression function, and that approximation or the target that I found is y cap. Okay. W0 and W1 are the coefficients. X is the input data, which is called as the independent variable here. And epsilon, I am considering it as the noise, that is the extra error that will come in. Okay. Why is the noise considered here? Because you can't exactly find y from W0, W1x because the data points won't be exactly on the underlying distribution. Instead, there will be slight error here and there. That's what I'm considering as noise, epsilon. Okay. So first thing is bias. You have to understand that the total squared error, it can be composed of three things. First thing is bias error. Second thing is variance error. And the third thing, this is the irreducible error or the noise. Okay. So bias and variance are what we can control when we are building a model. The irreducible error, this is not under our control. Whatever we may do, there will be this irreducible error that will creep into the model. We'll understand that as well, how it is creeping up. Okay. Let's see bias error first. In case of bias, we already told that it is the difference between the average prediction of our model and the true value we are trying to predict. That is the prediction that we are making y cap and the true value y. The difference between these two is what we are representing as the bias error. So for the whole model, how do you represent it? You will say it is the expectation of y cap minus y. This is how you represent bias error. What is expectation? Expectation or the expected value. We had seen that it is the average value when you see all the values of y cap minus y. Let us say I have the values of x and y. These are the values of x and y that I have. And y cap is what I predicted taking each of the x as input. So these are the y caps. What is the next step? I'll see the difference between y cap and y, and I'll take the expected value. The expectation is my bias. And what about variance? Variance, we already learned, it measures how much the predictions for a given data point vary across different training sets. In fact, not for a given data point, for the whole data, if you see across different training data sets, how do that vary? That is the variance. How do you calculate variance? Calculation of variance we had seen in previous lectures as well. Variance is calculated as expectation of y cap minus expectation of y cap the whole square. This is how you calculate variance. If you see the variance lecture, though we had explained this as well. So variance is calculated as expectation of y cap minus expectation of y cap the whole square. If you understand this logically, expectation of y cap is what you are actually what you want the model to find out. but y cap is what you found for this particular data set. So whatever is the difference that is occurring, that is when you, let's say you have one data set and another data set. In the previous lecture, we had drawn the graph, if you remember. We had drawn a blue and red graph, and we had shown you how the graph shown for blue and red differed, even though both were coming from the same underlying distribution. Okay, so that is how variance occurred. So in order to reduce, you have to reduce this term, which is expectation of y cap minus expectation of y cap the whole square. This is the formula for variance. You had seen this previously as well. And for bias, it is expectation of y cap minus y. Next thing is irreducible error. There is irreducible error. What is irreducible error? Let us understand it graphically, the irreducible error. Let us say this is my graph. This is my underlying distribution. Okay. Let us say my data points are these. These are my data points. Okay. Here you have to note that these data points are not exactly lying on my underlying distribution. Instead, these are slightly over or below. What does this mean? This means from these data points that are provided, it is impossible to find out exactly this distribution, exactly this function, to find out from the data points that we have sampled. That is just impossible because the data points are not exactly on that distribution. That's the whole point. If your data points were something like this, let us say if your data points were exactly on this, like this, then you had an outside opportunity to find out this exact function, because at least that the data is perfect. But what happens in case of the regression data that you have? The data comes from an underlying regularity, but it won't be exactly on that function. So because the data is here and there is an irreducible error that creeps into the model. Whatever be the number of data points that you take, let's say you increase data points, you got a lot of data points here. Even in that case, there is an irreducible error because the points are not all exactly on the function. Because of this reason, there is an error which creeps in, which is not at all under your control. Bias, variance, we're talking about all these, but what you can control is beyond this, because if the points are not even exactly on the function, you can't control that, right? So that's what we are calling noise or the irreducible error. And what is the final error? The final error, it can be calculated like this. The final error is bias square plus variance plus irreducible error. This is how you calculate the final total error. The squared bias error plus variance error plus the irreducible error. So here the bias and variance, this is where you have to be careful. If you try to reduce the bias error, your variance error will automatically increase. And if you try to reduce the variance error, your bias error will automatically increase. So if you try to decrease the first term, automatically second term is going to increase. Somewhere you have to find a balance between b square and v. That is what your task is, because the irreducible error that has crept in, that is not reducible. So you can't deal with that. So you can't make error 0. Instead, you try to make as minimal as possible. That is, you try to make the best approximation for this graph.